Hello, my name is Cheran Sivalingam, and this is my lab report for Lab 2. For this lab, we were required to observe the motion of an object in free fall, experiencing the forces of gravity and drag. For my object, I chose to observe a cardboard box. After I recorded this video, I analyzed the motion of the object in Tracker. As you can see in Tracker, we can see a graph of the Y position over time. The graph shows that the rate of change of the position over time increases as the box speeds up through time. But near the end of the time, the box reaches a terminal velocity, which results in the change in position becoming constant. After I analyzed the video in Tracker, I created two models in GlowScript to simulate the motion of the object. The first model I made accounts for only gravity as a force acting on the object. Some important points to note in the code are the mass of the box, recorded in kilograms, and the delta t, which was found using the size of each timestamp of the video. Here you can see the net force is equal to just the force of gravity. It's in the negative direction and is equal to the mass of the box times acceleration due to gravity times the unit vector, which is in the y direction. The velocity is updated using the momentum principle, showing that the final velocity is equal to the initial velocity plus the net force divided by the mass of the box times delta t. The position is also updated using the formula. The final position is equal to the initial position plus the velocity of the box times delta t. Running this model shows a consistent change in position as the box is speeding up, and it shows the velocity to be constant, the change in velocity to be constant throughout, indicating a constant acceleration. However, if we view our second model, we now account for two forces. The force of gravity is still there, but in the opposite direction, we have the force of drag. So this is calculated by using the proportionality constant, which is 0.139. This was found by trial and error to see which proportionality constant resulted in a similar position, end result position as the observed video. And this is multiplied by the magnitude of the velocity squared. So now we have the force of drag and the force of gravity in opposite directions, both affecting the motion of the box. If we run this program, we see that the position of the graph is different and is actually a lower position than what was predicted by the model that showed just gravity. And if we see the velocity versus time, we see that the change in velocity is now no longer constant. It starts constant but begins to change until it tapers off here, which is where the box reaches terminal velocity. If we observe the graph, we have three graphs here. We have the observed position, which is taken directly from Tracker. We have model 1, which uses only the force of gravity, and we have model 2, which accounts for both the force of gravity and the force of drag. As you can see, model 2 is much closer to the observed motion than model 1. This is because, of course, in real life, the force of gravity is not the only force present. Both the force of gravity and the force of drag are present, which results in the position of the final position of the box being lower than what using just gravity would have predicted, because the force of drag and the force of gravity are in opposite directions. So the net force ends up being slightly smaller in the observed position and model 2. So what does this mean? So as you can see, observing the velocity versus time of the first model and the second model, we can see that the first model does not predict a terminal velocity and rather predicts a constant change in velocity throughout the entire time. Whereas you can see in Model 2, the velocity begins to taper and stay relatively constant near the end of the time, indicating that Model 2, which accounts for both the force of gravity and the force of drag, is the one that predicts terminal velocity. Terminal velocity happens when the force of drag pointing up has exactly balanced the force of gravity pointing down. What does this mean for the net force? So this means that the net force is zero. If you have a force in one direction and a force in the opposite direction and their magnitudes are exactly the same, that means that the net force is now zero, which makes sense for the concept of terminal velocity, because if there is no net force, then the velocity should stay constant because there's no acceleration affecting it. So what if? So in our Model 2, we can see here we started with no initial velocity, and we reached a terminal velocity of around negative 2.5 meters per second. Now, if we look at a model that I ran already with the same model of Model 2, except with an initial velocity of around negative 4 meters per second, we see that the starting position is different, but the actual end result motion ends up being exactly the same at negative 2.5 meters per second. This shows that no matter what the initial velocity is, whether the object is thrown or simply dropped as we did, the terminal velocity is not affected by the initial velocity. It is instead only affected by the properties of the box itself. Thank you. This is my lab report.